Alright, so in this lesson we're going to look at what would happen if we do have non-conservative forces acting in a system. So if we have non-conservative forces acting in a system, work done by non-conservative forces changes the total energy content of the system. One of the most common non-conservative forces we deal with is friction. And if friction is doing work on a system, that work is, I would say, always negative. This is one of the few times in science that I would say always. I can think of very few scenarios where friction being done on a system applies positive work. The only thing that I can think of is if it was something like a rotating disc connected to another rotating disc and friction between the discs caused one disc to spin. There are scenarios where friction being done on a system is not doing any work. That'd be a situation where friction is acting in a direction that's perpendicular to the direction of motion. Well, anyway, if we're going to deal with a non-conservative force, we got to rewrite the equation as shown here, that potential energy initial plus kinetic energy initial equals work done, or plus work done by any non-conservative force equals potential energy final plus kinetic energy final. Now, this is slightly different than the way I believe your textbook writes this. I think it talks about the difference between final energy and initial energy is the work done by non-conservative forces. I think of it this way, as that this work done by a non-conservative force is just another term in my conservation of energy equation. So let's go back to our skier problem. And remember, with the skier problem with friction, this is actually kind of a middle difficulty problem. We had those two forces are the key forces, or the key piece of information. Remember, I had weight, normal force, and frictional force. Going to travel 50 meters down the slope. The one thing that I don't need to worry about really is the 70-degree angle when we look at our work done by non-conservative forces. The distance I'm interested in really is this initial height. How high am I up off the horizontal, which is 50 meters times sine of theta, this side of this right triangle here. So first thing to point out, if I start at rest, my initial kinetic energy is 0. If I end up at the bottom of my ramp, my final potential energy is 0. So really, initial potential energy plus any work done by non-conservative forces equals final kinetic energy. So I have mgh initial minus F times x, the negative because friction is doing negative work, equals 1/2 mv final squared. So next thing I've done, multiplied everything by 2 to get rid of the half, divided everything by m, and then I square rooted everything, and I would end up with the same result we had before, the 14.2 meters per second. This result, at least in this way, I think is a little bit easier to get to this result using conservation of energy than it was to use work energy theorem. You can get to the same result in more than one way. So friction is just one non-conservative force. It's the one we come across most frequently. There are other non-conservative forces that we could be dealing with. You could be pushing something up the ramp and figure out how high it goes, or maybe tension or rope pulling on it could be a non-conservative force. Depends really on what are the other forces acting on the system, what goes into here. So really what we have when we have our full equation here is we now have a way to account for initial mechanical energy of the system, final mechanical energy of the system, and any changes to that energy during the course of whatever happened to that system.